Alright, I'm going to start here. I'm going to use a little bit of a blackboard here. And what I'm going to posit here is first, mathematics. Welcome to my bad handwriting day. Mathematics has existed across many cultures. And the goal of this course is to really be to break apart what these cultures shared. If we look historically, mathematics spread with the trade routes along the old spice routes and the Silk Road, and really followed some of the language migrations historically. There's a lot of evidence that the first written documents were done to work with mathematics, specifically counting days. So mathematics gets developed in not almost every culture. Every culture develops tools for using quantity and dealing with mathematics. The mathematics we learn were collected together mainly from Greek, Arabic, and India sources, and then passed through the Greek and Roman empires into the dominant culture in the world right now. But there are traditions outside of that knowledge that are still valid. There's a lot of research done in what's called ethnomathematics, which looks at how cultures solve problems. And what we're going to do is break it down into pattern recognition, as one of the fundamental roles of mathematics. And that's what the first chapter deals with is how do we make conclusions about patterns. And we see this, that early numbers dealt with counting things and moved to measuring things. And somehow the same idea of a number had to be used for these two things. And in that was pattern recognition. In fact, some of the biggest jumps in mathematics didn't come from the counting, but came from the measuring and its sister science of geometry. And so there's a link between geometry and what we do with mathematics. But chapter 1 will deal with pattern recognition. At the same time, we develop language around the patterns. And modern mathematics is a slowly evolving set of symbols that are translated one way. And we will look at what language means a little bit in chapter 2, where we deconstruct mathematics into not number, right, this is what happened to number, but collections of objects. And those collections of objects are going to be called sets. And so our first two jobs is to really break down everything we thought about mathematics before and try to strip it into some basic ideas, recognizing patterns and coming up with a language around patterns. Now, number is historically how we first found these ideas. But a lot of the ideas of modern mathematics transcends numbers. Right now, we're all talking about AI, which use large language models, which at their core are a whole bunch of matrices. And a matrix is a way of pointing a vector. And we've been able to create a collection of objects which are within language, and map them back to a vector. So there's this progression where we counted things, we then measured things, and we found patterns in these counting and measuring, and we built a whole bunch of symbols to go with it. And then we said, well, these symbols can talk about more than number. And our goal is to break it down into these basic symbols. Then when we go back into chapter 6, we're going to focus on number and quantity. And specifically algebra. And then we end with statistics to end the course. So these first couple of chapters, people will sometimes struggle with, because we are taking ideas that you are familiar with and we're looking for deeper things inside of them. And a lot of times when we do that, we have to break them down in pieces. So what we're going to do here is we're going to start with the lecture on problem solving and critical thinking. And we're really going to start this first chapter with some definitions. So we're hoping that we can understand and use inductive reasoning, and we can understand and use deductive reasoning. So starting first with inductive reasoning, which is a process of making general conclusions based on observations of specific examples. So we have some specific things that we then want to conclude about. At the end, if we ask ourselves why people invented mathematics, we have to look that they wanted to make predictions. Some of the first mathematics were calendars. And if you were a wandering group of people, or some of the first people to grow food, and you're living near or within the tropics, seasonal changes are not as predictable as we would say up in the more northern climes. The change in sunlight is not as dramatic between the seasons, and the perceived weather changes come and go. Just like in the Northeast, we would have sometimes that extra summer that was sometimes called Indian summer or natives, the third or fourth harvest. That doesn't happen every season. There's some fluctuation in it. And these fluctuations and seasonal changes made it really hard to actually tell time for early cultures that were very close to the equator and didn't have as much of a change in the daylight hours. And so counting days to figure out when the Nile would flood again, to figure out when different seasons would come about, became a very important thing to predict future events. Inductive reason is that you look at something and you want to predict future events. We as a society are fairly cursed right now with that our technology does a lot of heavy lifting for us, that we are a little disengaged from some of the things that our technology is based off of. And calendars is a fairly fascinating one. Since the 1930s, the ability to freeze food and store food for long periods of time and to transport food quickly and freshly has led to that we don't eat seasonally anymore. We go to a grocery store and get things. My grandparents' generation knew when seasons were changing because different foods were not available anymore. As a child, you would go get fruits at the end of summer, beginning of summer, depending on what fruits were coming about. That is getting less and less prominent. I think up here we still have a very good apple season for the fall, but that was more tradition. Distangling from these periodic events means that we lose these specific examples and observations coming about. So inductive reasoning is these things that were invented and used to develop mathematics to look at how we could predict future things based off of the past happening. And so that works within two things. We make a conjecture or a hypothesis. And that is a conclusion that, hey, we looked at these things, right? We look and we say every 300 days, 360 days, the Nile will rise and flood. And that flood will last for 3 weeks. And then when it subsides, the soil is filled with silt and is very easy to plant for, right? And the Egyptians worked really hard on building a calendar because they needed to know when the Nile would flood, and then when the floods would recede, so that they could plant their crops in the fertile ground that came about. And that predictability came from counting. So their conjecture and hypothesis was, we've marked out each day, and after so many days have changed, the Nile floods. And as time went on, these calendars weren't as good. There were counter examples, years where the Nile did not flood on those days, and they updated their calendars. Right? And so we have a conjecture and hypothesis that a conclusion was formed as a result of inductive reasoning, which may or may not be true. A counterexample then is a case for which the conjecture is not true, and it will prove your conjecture false. So you can make these statements based off of observation, but if you find one that's not true, your conjecture is false, and you have to go back and you have to look at your observations again and create another one. So here's a strong inductive argument. So in this example, we take a sample of 380,000 freshmen at 772 four-year colleges. In fact, I'm just going to read this, and then I'm going to go in and look at the detail of it. One of the other things we have to work with in mathematics is when I want to give you a real-world example, I'm going to have to do it as a word problem. Word problems can seem dense. The best way to approach a word problem is to read it all the way through first, and then tear it apart. Some people have been taught to pick out the numbers and then try to figure out together. This was test-taking strategies to get through tests quickly. We're looking at what things mean and how to use the things. So what we're going to do here is we're just going to read this slowly, and then we're going to take this reading and use it to look at the different parts of reasoning. So, in a random sample of 380,000 freshmen at 772 four-year colleges, 25% said they frequently came to class without completing readings or assignments. We can conclude that there is a 95% probability that between 24.84% and 25.25% of all college freshmen frequently come to class unprepared. Now, the density in this has to sometimes be parsed, right? There's a lot of numbers coming across. For example, the four-year colleges, four-year college doesn't matter as a number. It's an identifier for the type of thing. The numbers that really come into play for me, if I were looking at this, is the number of freshmen and the percent that they said came frequently to class. The number of colleges then ends up being what is called the technique called random sampling. And we'll look at this in chapter 12. But in random sampling, each member of a group has an equal chance of being chosen. So we can make predictions based off the random sample of the entire population. And so we have a random sample. We've taken these 380,000 people, and 25% of them said that they frequently came to class without completing the reading. Now, the statistics will tell us that means there's a range of people. That 25% is what we have observed, and by dealing with random sampling, we can make the argument that there's a 95% chance that between 24.84 and 25.25% of all college freshmen frequently come to class unprepared. So where the inductive argument comes from is, I've taken 380,000 freshmen. That is not all of them. They're my external observation, and I'm using it to predict what would happen for all college freshmen. And so that's what we mean by an inductive argument. If we look at something and we apply it to a larger scheme. Now, a weak inductive argument, one that falls easy to counterexamples, well, again, I'll read this first and then we'll look on this. Neither my dad nor my boyfriend ever cried in front of me. Therefore, men have difficulty expressing their feelings. Don't know, it's been World Cup time, and having been with my wife being English and having watched many a World Cup, I will say that I have seen men expressing their feelings. So this conclusion is based off of two examples. And it's not random, nor is it very large enough to represent all men. So the argument is weak. In fact, it takes one counterexample to break that. And I just gave you a counterexample, right? In the World Cup games, I think watching Holland and Jude Bellingham show friendship and camaraderie was an expression of feelings. That is a counterexample to the two given here. Now, inductive reasoning isn't always working with complete randomness. Sometimes we can be given a pattern. In fact, a lot of times this gets taught in number patterns before it gets taught into other patterns themselves. And so here is an example where we have the numbers 3, 12, 21, 30, and 39. And we can look at this sequence of numbers as being kind of the observation we have. And we have to ask ourselves what's happening between each set of numbers. And so we look at this and, well, going from 3 to 12, it's increasing. 12 to 21 is increasing. 21 to 30 is increasing. And 30 to 39 is increasing. So the next number should be larger than 39. That's the first pattern we recognize. Then we have to ask, well, how is it increasing? And if we go from 3 to 12, usually the first thing to look at is additions. And so there's a gap of 9. And so I'll look from 12 to 21. Is that also a gap of 9? And it is. And then I look from 21 to 30, and that's 9. So it looks like each number is 9 more than the previous number. So the next number in my sequence should be 39 plus 9, or 48. And so that is a form of inductive reasoning. We have a pattern of numbers coming about, and we're asking ourselves what the next numbers would be. And that could continue on. We could go from 48 plus 9 more would be 57. Now here is another example of a pattern of numbers. And we notice it starts with the same two numbers as the previous example, 3 and 12. And so we notice our numbers are getting larger. We expect the next number to get larger. The difference between these first two numbers is this first number and our last number in the sequence that we have is larger. In fact, it seems to be getting larger and larger. And so one of the things we can look here is what is happening to the numbers. And so 3 to 12 is plus 9, but it's definitely more than plus 9 here. And so we can ask ourselves, well, how else can 3 get to 12? Well, if I'm getting larger, the next thing I would do would be to multiply, kind of going up and down the order of mathematical operations. We start by learning addition, then we learn multiplication, then we learn powers. So I'm going to try multiplying. And well, I have to multiply 4 to get to 12. And so I come over here and ask myself, hey, if I multiply 12 by 4, do I get 48? And I do. And if I multiply 48 by 4, do I get 192? I definitely run to my calculator at this point. But we're noticing each number is then multiplied by 4. And so my next number is going to be 768 multiplied by 4, or 3072. And this is a pattern going. So in each of these cases, we had to use the pattern that was in front of us, and then we had to ask questions about what was happening with the pattern. Notice I have approached this by talking about very general things first before getting into the specifics. A lot of times when doing pattern recognition, we'll see the same type of patterns over and over again. Like we said, hey, 312, I'm adding 9. And so we'd come back here and say 312 adding 9, and it fails right off the bat. But if we start slowly and circle our way in, noticing everything is getting larger, everything is getting larger, and then we ask ourselves, well, how much larger is it getting? Because not all patterns will always have to get larger. Now here is another here is a sequence of numbers. Now, this one's actually famous. This was in one of the first textbooks on mathematics in the Western world, called Liberal Abaci by Fibonacci. It was published in 1202. And these numbers are actually called the Fibonacci numbers. They solve a very interesting problem. Let me switch over to here. The question that Fibonacci asked was, supposing you have one pair of rabbits and it takes a month for them to breed. So you start with a pair of rabbits. A month later, they're going to breed, and that's going to give birth to another pair of rabbits. So now you have 2 pairs of rabbits. This first group is still going to be able to breed, so they're going to give you 1. But this second group, this one that got added into the 2 here, is going to need to wait a month before it can breed. So in your 3rd month or 4th month, you're going to have 1 plus 2, or 3 rabbits. Now the 2 here are able to breed, but the additional one that came into this 3 can't breed yet. So they're going to have to wait a month until they can breed. And so with that next month, these 2 will give you rabbits, and then these 3 will, and you get 5. And so the question that was asked in the textbook is, given a pair of rabbits, and it takes them a month before they're fertile and can breathe, how many rabbits would you have after so many months? And the series ended up being, you have to start with 2 numbers, your first 2 months, and add them together. Then you take the next 2 numbers and add them together. Then right, so 1 plus 1 gives me 2. 1 plus 2 gives me 3. 2 plus 3 gives me 5. So the next number in the series would be 3 plus 5 is 8. 5 plus 8 is 13. 8 plus 13 is 21. 13 plus 21 is 34. 21 plus 34 is 55. And so on. Now, because the Fibonacci series came from this idea of growth with a delayed start or a delayed fertility, this actual sequence of numbers appears in a lot of things. And so you'll hear people talk about Fibonacci numbers. Fibonacci numbers create the golden ratio, which is seen in a lot of art. And so this was a pattern that was very interesting to discover and find. From one odd question, that pattern got recognized in other places. But even looking at this one, it's a little bit harder to see sometimes, because we're not doing one thing to each set of numbers, but we're actually using a pair to move across. And it always has to start with 1s for this to work. And so this is another inductive reasoning. We use the previous numbers to tell us how to move through and create the series longer. Sometimes we can have more than one solution. Notice that we have not enough numbers here with 2 and 4. I could say 2 plus 2 is 4, but 2 times 2 is also 4. So there are many different patterns that can come from that. When you have not enough information to go through, you end up with multiple solutions that could come about, and it takes more observations then for you to actually have your reasoning come across. I like that they use this inverse space idea. Where is it two faces or a cup? And the same thing kind of happens here. When you have a small pattern like this, the boundaries to where the answers can be touch multiple types of answers. A non-numerical way of looking at pattern recognition, this is definitely a good way of looking at mathematical thinking, is to look at some geometric relationships. Now, in our shapes here, the one thing I'm going to notice is I go from circle to square to circle to square. But also, while it moves, the orientation of the 3 dots and the 1 dot changes. Right here, 3 is on the left and 1 is on the right. Here, 3 is on the bottom and 1 is on the top. Here, 3 is on the right and 1 is on the left. And here, 3 is on the top and 1 is on the bottom. So it's rotating. Right? It rotates up to this position. This rotates down to this position. This rotates across. So my 1 dot is going to be on the right, just like it was at the beginning. And I'm going circle, square, circle, square. So this is going to be a circle. So this pattern is going to end up being back where it started on the next iteration. And that's what we get coming across. But notice how in my language for this, I'm going back and forth with the observations, looking for all the things that change between each one so that I can predict the change. So inductive reasoning is based off of observations and seeing where the observations take you. Deductive reasons is proving a specific conclusion from some general statements. And that conclusion is called a theorem. So we can take some everyday situations. One player to another in a game of Scrabble, you have to remove those 5 letters. You can't use Texas as a word. The general statement is, in Scrabble, all proper names are prohibited in Scrabble, and Texas is a proper name. Therefore, Texas is prohibited. So, deductive reasoning or deducing uses clues and laws and specific, what mathematicians call axioms. All right, this example here works out nicely. And what I'm going to do here is we're going to look at these rules. It's going to say select a number, multiply the number by 6, add 8 to the product, divide the number by 2, and subtract 4 from it. So I'm going to work these out, but I'm going to do it in steps. Because having it all printed there without steps, we miss some of the motion. So our steps are going to be select a number, now if we were in class, I'd just have someone scream out a number. What I'll probably do is cry a little bit and throw a die or something. Alright, we'll multiply the number by 6. Why did that switch back to it? Come back here. There we go. Sorry. I'm going to write this on the board here. So we're going to want to multiply it by 6. Then we're going to add 8 to the product. And the product is just our way of saying the answer from the previous 2 steps. These are all kind of steps. I'm going to divide the sum by 2. And then I'm going to subtract 4 from the quotient. Now I'm going to make some notes here. The product is what comes out from an answer from multiplication. So this word product is telling me the answer from step 2. The sum is what we talk about from the answer of addition. So this is asking for the answer to step 3. And the quotient is what we talk about in an answer from division. So it's asking for the answer from step 4. So I want to select a number. So we're going to select 9. I'm going to multiply it by 6. So 9 times 6 is 54. I'm going to add 8 to the product, so 54 plus 8 is 62. I'm going to divide the sum by 2, so I'm going to divide 62 by 2, which gives me 31, and I'm going to subtract 4 from it. Equals 27. And so that's what these things mean here. So I'm going to go back to the slide now. And so the slide has done this with some different numbers. And so when we do it with 4, we end up with 12. When we do it with 7, we end up with 21. And when we do it with 11, we end up with 33. What we want to do here is use some deductive reasoning to figure out what it's going to be. And so what I'm going to do here to get the deductive reasoning going is I'm going to do these steps again. I'm going to do them in yellow. So I'm going to select a number, and I want to pick any number. So I'm going to use the letter N to be any number. And I'm going to multiply it by 6. So step 1, we pick n. Step 2, I'm going to multiply n by 6. So I'm going to have 6 times n. And I'll write it in this format. Step 3 says I'm going to add 8 to the product. So 6n plus 8. And so notice each of these words or steps I'm turning into a symbol. Now I'm going to divide the sum by 2. I'm going to write this as a fraction bar because it's a better way to write divisions. And then subtract 4 from the quotient. So all said and done, I have something that looks like this. Without knowing my number, I'll write it bigger here, I have a mathematical way of representing the steps we did. In fact, that's what this language of mathematics tends to do, is it takes steps and puts them into a symbolic form. Now we get some benefits from that steps because we have orders of operations we can do and things we can do to simplify this. I can make this look more simple. And I can do that by going, okay, well, if I'm dividing all of this by 2, that's the same as dividing 6n by 2, which is 3n, and the positive 8 by 2, which is 4. And then in the 4 minus 4 is 0, so I'm left with 3n. By using my rules of how these operators work, by following the order of operations, all of these steps end up saying 3n. So instead of going through all of these steps, my deductive reasoning says, well, if I select a number and I multiply it by 3, so 3 times 9, I get 27. And that is my end. Let's look at some of the other things from the slide here. So if I go back to the previous slide, if I take 3 times 4, I get 12. If I take 3 times 7, I get 21. If I get 3 by 11, I get 33. What this is really saying is the rules of mathematics let us do deductive reasoning for the steps that we would do to build or construct something out of numbers. If we have to do a certain routine with numbers over and over again, we process a payment coming in using the same percentages and the same deductions, but the payment changes. Can we change it into a formula that's simpler than going through each step? And so that's how deductive reasoning works mathematically here. So that's section 1. Go back, reread the chapter, look at some of the examples in the book. Start playing with the homework in section 1. If you have any questions, fire me off an email.